My name's Kelley France. I'm a data technologist at American Fidelity, and I think actually Megan and Mark Nance were here a few months ago talking about some of the really cool projects that our team's been working on, and in that vein, we do want to tell everybody we're hiring. We're hiring a data scientist, an experienced data scientist, and some of the description is up here on the slide. If you're interested, definitely go to that website and apply. We'd love to talk to you. American Fidelity has been really great to me. They really do the work-life balance thing right, in my opinion. They're the most flexible company that I've ever worked for, and they're consistently named in the top 100 companies in America by Fortune. So it's definitely a good deal. Okay, so for this talk today, I'm going to start out with, obviously, my inspiration for the project, but we're going to talk a lot about, in the beginning, the biological processes that have to do with food allergy, and then dig into the mathematical model a little bit, and then move on into some of the coding and some of the more technical pieces of the problem, I suppose. So my inspiration for this project is my daughter, Evelyn. And why aren't you working? Is it going? Nope. Sorry, guys. There we go. It's not mirroring that on my screen here. Anyhow, my daughter, Evelyn, she's 4 years old now, but when she was 1, we gave her a bottle of milk, and within 30 minutes, her face had swollen, she was having trouble breathing, she was vomiting, and we were rushing to the emergency room. They sent us home that day, thankfully. A good round of steroids and antihistamines were able to knock it out, but they sent us home with a prescription for an EpiPen and told us to go see our pediatrician. So shortly after that, not surprisingly, she was diagnosed with a severe life-threatening dairy allergy. And shortly after that, I ended up quitting my job. The daycares just weren't a safe option. There's milk. There's a lot of milk in daycare facilities. And so we had to pull her out. And shortly after I quit my job, I decided I was going to go back to school. I was going to finish my degree and go back and do something that really interested me, and that was mathematics. So when I went back to school, I started doing research with Dr. Laverty, he's here today, and Dr. Brittany Banish in biomathematics. And so naturally, I wanted to study the thing that most frustrated me and baffled me, which was food allergies, so that's what I did. Now, currently today, Evelyn's been desensitized, so has anybody here heard of oral immunotherapy? A few people, yeah? Okay, so basically what that is you start out with a really small amount of whatever the allergen is for the person, and you gradually build that up until they're completely desensitized from the thing that they're allergic to. So in her case, she started out with like 0.3 milliliters of a watered down milk solution and built up to 8 ounces of whole milk a day. So that's where she's at now. So now she's completely desensitized. She can eat whatever she wants. She goes to school just fine. We don't have to take any special precautions. It's pretty amazing. And so we have this situation where the immune system is adapting, and I don't want to say changing because I don't know how much it's changing yet. That's kind of what this research is about. But it's adapting and becoming desensitized. And so the question for my research is, how does oral immunotherapy impact the immune system of an atopic individual? And before we go too deep, I have to thank my research advisors, Dr. Brittany Banish and Dr. Sean Laverty. They really gave me a good solid ground to start on here and have been just really, really amazing throughout the process. And the University of Central Oklahoma, all of those departments paid for all of the travel funding for the project, so I've been able to go all over the United States and speak at a lot of different conferences, and it's been a really great experience. So as we get started here, let's talk about what's happening as far as the biology. So if you're an atopic individual, then you have an allergy. You have a food allergy. And let's say you have a dairy allergy. And so you ingest some dairy, and the dendritic cells that live on the surfaces of kind of our mucosal layers in our skin, they come into contact with the milk and they go, oh, okay, I'm going to take this to the nearest T cell and see what it wants to do with it. It's basically just a messenger. And in an allergic person, the nearest TH cell, helper T cell, is a TH2 cell. And what these TH2 cells do is they release a cytokine, which is also a messenger, but it's called IL-4. And they release all of this IL-4 when they get the milk signal. And in the same area, we've got B cells. And the B cells produce different antibodies, and the antibodies kind of run the show on how to attack whatever the invader is, right? So in this case, I have the B cell named for the type of antibody it's producing. So we've got an IgM B cell, producing B cell. But when it comes into contact with this IL-4 cytokine, it undergoes a class switch. And when it undergoes this class switch, it switches to an IgE producing B cell, okay? And the structure of the IgE is built in such a way that when it attaches to the mast cell, it triggers the mast cell to dump all of the histamine, and that's what's causing anaphylaxis. Now, let's see, where are we at up here? Yeah, so there it's dumping all of the histamine, resulting in anaphylaxis. The main takeaway here, TH2 produces IL-4, which causes the B cell class switch to an IgE. Now, in a non-allergic individual, somebody drinks milk, a dendritic cell goes to the nearest T cell, and it's a TH1 cell instead of a TH2. TH1 cells release IL-2, which cause a class switch to IgG instead of IgE. IgG binds to the mast cell, nothing really happens. This is what's going on in us normally when we don't have a food allergy. And so what my model is going to look at is this process right here, the part that really kicks off the allergic reaction. So we're going to be looking at the dendritic cells, the cytokines, and the helper T cells that are involved in producing the IgE and the IgG. So there's been a very steep increase in the number of food allergies in children over the last decade. They don't really know what's causing it. One of the theories is the hygiene hypothesis. And so to explain that a little bit better, you know, we think back to what we just saw. TH2 produces IgE, which causes anaphylaxis. TH1 produces IgG, which is a normal reaction. So IgG attacks viruses, IgE attacks parasites, and when we're born, we're naturally born with more TH2 than we are TH1. And that's just so that our bodies don't attack our mother's cells when we're in the womb, and vice versa. So when we come out, we naturally have more TH2 than we have TH1. In a normal person, what happens is this levels out and the TH1 eventually takes over and the TH2 just kind of stays down here in a normal range, hanging out waiting for parasites, right? So the idea here is that as a society, we've become a lot cleaner. We don't have as much disease and infection anymore. And because we don't have that exposure to the virus and that bacteria, our TH1 cells in certain individuals never have a chance to really catch up and begin to produce more than the TH2 cells. So that's the idea that my model is kind of exploring right now, this idea of oral immunotherapy and the hygiene hypothesis. How are milk and virus working together to change a person's response to an allergen? All right, the model. Who remembers differential equations? Anybody? Yay, a few of you. Okay, so this is the model I've built so far. It's an ordinary differential equation. It's a first order initial value problem, and we're not going to go too deep into this because there's a lot up there right now, but we'll talk through some of it here, mainly the populations that we're measuring. So the population we're starting with here is a dendritic cell with milk. This is a dendritic cell that's come into contact with milk. Now, if we go down one, we have a dendritic cell with IL-4. That is a dendritic cell that's come into contact with milk, and then it's come into contact with IL-4, which is basically signaling it to create more Th2 cells, okay? So that's kind of how this is all feeding in together. If you look at the second piece of the dendritic cells with milk, you can see here that this is the rate at which dendritic cells with milk come into contact with IL-4. And so when this happens, the dendritic cells with milk, that population is decreasing, but the dendritic cell with the IL-4 is increasing. So that's how these are connected. You can see that in the first equation and in the second equation. And then as you go down, you can see, like for the IL-4 cytokine right there, the T2, the Th2 cells are directly impacting the population size of the IL-4 cytokine, which makes sense, right? Because the Th2 cells actually produce the IL-4. So if we have more Th2, we have more IL-4. And that's kind of how this is operating here. So onto the code. I just put some snippets up here. I don't think it's important that we go too deep into it unless you guys have a ton of questions. We can absolutely talk about it. But what I did was I used RStudio. I used a package called DE-Solve. And in that package, there is a function called LSODA, and I call it LSODA, and I have no idea if that's what you're supposed to call it, but that's what I call it. And basically what it does, the cool thing about it, it's kind of an interface to the Fortran language, and so what it does is it switches its ability to switch between stiff and non-stiff solving methods. So if you're seeing like a really big rate of change, it can go, oh, this is changing a lot. We really need to try solving it this way so that you can get more accurate results. And so that's what I used for this. And here on the left, you can see the parameters. Do I have the parameters? Okay, good, this matches now. All right, so we've got the parameters on the left, and that's the list of parameters we saw earlier, but it's the actual values that we're assigning to them. And these values come from a lot of different places. They come from other math models. They come from research papers, medical journals. These numbers are extremely difficult to find. They're extremely difficult to estimate, and that's one of the biggest challenges that I face, and that I think most people working with differential equations in biomathematics face, is trying to find a good estimation for the rates of change for these populations. So there on the left, we've got the parameters. You'll see for the first four, I just have 0.5 stuck in there. That is a guess. I have no idea what those numbers are yet. In the middle, we're actually defining our differential equation. So that's our full differential equation that we saw on the previous page. Next to that, we've got a vector of timestamps. This is just telling us how often we want to check the change in population. So right now, we're doing a 0.1 time step just so that we can get kind of a finer, it makes the plots look better. So, and then we have our initial conditions. That's the X start, okay? So that's where we're starting out. We're starting out with, like, let's see here, one dendritic cell with milk. Well, that makes sense. We've got one dendritic cell. It's got milk. Let's see what happens. And then lastly, we have the output. So we take all of those things and we put it into the LSODA function, and it spits out results like this. And they're pretty straightforward. You know, you've got the time on the left, and then you've got the population size of each one of those populations that we defined earlier. So we've got the dendritic cells with milk, a dendritic cell with IL-4, a dendritic cell with IL-2, Th2 cells, so on and so forth, right? Really basic, really simple. Problem is there's about 10,000 rows here, and then we've got 8 variables, so we end up with about 80,000 records. So obviously, you know, just combing through a table isn't going to be super helpful. So we want to visualize it, and when we visualize it, what we see, I mean, it makes sense. Basically what I did here was I ran the model with no milk and no virus. So if you lived in a bubble and you were never exposed to anything ever, this is what my model says would happen. And it makes sense based on the way I put it together. You know, the Th1 and the Th2 cells are growing at the same rate. We don't have any exposure to milk, so we don't have dendritic cells with milk, so that goes down to 0. Since we don't have any dendritic cells with milk, we don't have the IL-2 and the IL-4 coming into play. So a lot of things are going to 0, and then everything else is kind of leveling out. That makes sense. We wouldn't expect any big changes because we're not introducing any big changes, if that makes sense. And next what I did was I went ahead and added milk. And the way that we added this was kind of in a stair-step type function, because the way that it's done is for 1 week you take this amount, then you up it for the next week, and so on and so forth until you get to that protein level that you're looking for, the milk protein level, and then you take that every day. And so it's kind of discrete, right? And it's not continuous. It's kind of, it happens here, it happens here, it happens here, it happens here. And what we see here is that introducing the milk without the virus, there's no virus here, it's blowing up our Th2 population. You can see it's up there, what is that, a little over 4 trillion, whereas, before we're in the millions. So it's tripling it. I mean, I don't know, tripling it, doubling it. What's the power here, Dr. Laverty, do you know? Okay, 10 to the power 3,000. So yeah, so it's increasing it quite a bit. And so we kind of see something that we think, okay, yeah, that makes sense that would happen. The dendritic cell with milk would attach to the IL-4, which would cause it to make more Th2 cells and kind of continue that process. But it's also a little counter to what I've experienced personally with my daughter's oral immunotherapy, in that, we had this increase in Th1 and something leveled off there. And so I think what we're missing here is that virus and that hygiene hypothesis. So the next step really is to introduce a virus and see how these graphs change and really understand a little bit more about how the milk and the virus are interacting together. So this is really, really new research for me. I just started last August, so this is brand new. So next steps for me, I really want to refine this model. I need to look at some other immunological models and try to get some information on how they are presenting some of these interactions between the dendritic cells and allergens, or dendritic cells and virus, things like that, and then introduce the virus component and evaluate those results. So in thinking about these next steps, I'm a math nerd, but I'm also a data enthusiast. So when I think about these problems, I'm naturally drawn to think about them in terms of data, especially since I end up with all of these massive tables full of numbers. So why not, right? And so when we think about the challenges to overcome, one of those that we already talked about was parameter estimation. And so for the next few slides, we're just going to talk about maybe some of the challenges, where I'm thinking about going next. I'm still in the planning stages, but I have a room full of really, really smart people here today, and so I'd like to capitalize on that. So if you guys have any suggestions, please let me know. So parameter estimation, estimate and test. That's what you do. You plug in a number, and then you run the model. And then you go, does that look right? I don't know. Let's research that. And then you go, okay, no, that's not right. Let's go back. And you do this over and over and over and over and over again. And really here, for the parameters on the right, a lot of those you can find in medical journals or in other write-ups about other math models, other biomath models. But these ones on the left, B, C, J, and K, these are things that you're probably not going to find in a medical journal. So like J, the rate at which naive helper T cells come into contact with dendritic cells in the lymph node that have IL-4 attached. There is probably not somebody that's calculated that. I mean, if there is, that would be amazing because I need that number. But there probably isn't. So we can look at this in a couple of different ways. You know, it's really easy to write a simple loop and just test a whole bunch of scenarios. And so we do that. We write a simple loop. We get all of this data, but then we have so much data, and there's so many dimensions, and it just gets really hard to visualize it all and to really find the information that you're looking for. And so my thought was, well, can we use some sort of machine learning mechanism to estimate these parameters a little bit better? For example, we could talk about, you know, because we are working higher dimensions, and that is a problem. We could talk about PCA, right? Trying to figure out what's going to be the most important piece of this puzzle for us. That would be extremely helpful. Another thing we could do, you know, I don't know, random forest, why not? Let's test everything on B, C, J, and K from 0 to 1 at different intervals, and, you know, train a model and see if we are getting population, you know, which bucket is the right population size that we think is true to what we would expect in real life. Or maybe that is overcomplicating things greatly, and we just, you know, run a massive for loop and then bin all of the results and look at trends from there. So there's a lot of opportunity in this part of the problem to really start digging in and looking at the data that we're producing and then using that data to make a more informed decision outside of just combing through research papers. So once we have a pretty good model, something that we feel like is estimating what's really occurring in the body when milk is introduced or when a virus is introduced, we can then start running the model on different treatment levels. So for us, treatment would be milk and virus. And so we would start varying those treatment parameters and looking at the outcomes. Again, if we're treating someone, there are an infinite number of ways to accomplish that. You know, you could start out with the way that they're introducing milk now. You could completely change it and start with a really high dose and then move to a low dose. You could separate it out over months instead of weeks. You could, you know, there are a million different options. There's no way to test every single one of those. But I think when you have a good approximation of a biological process and you are producing mounds and mounds and mounds of data, pseudo data in this case, you know, you're basically, you're going through clinical trials without going through clinical trials, right? You know, you can do a treatment on a person without doing a treatment on a person. So you have a lot of options there, and if we apply some of these tools that are newer, I shouldn't say newer, random forests, neural nets, things like that, you know, I feel like there's a lot of possibility there. And again, I'm in the very beginning planning stages of this, but I'm excited to move forward with that. If any of you have any really awesome ideas.
How long have you been working on this?
Okay, he asked how long I've been working on this. This particular project I've only been working on since August. And before this, I was working on a mathematical model for HIV in children. So, yeah.
Okay, you have a model, but do you actually go back and, for example, with your daughter, do you actually measure those levels that are occurring?
No, that's something that maybe a biologist would do. So like a biologist would collect all of the data and do those types of like lab tests. I would take those numbers from them and put them in R and process them that way. Does that make sense? It's more of, I'm doing more calculations rather than like actually going and doing a blood test or something. They do the way that they diagnose food allergies today is by testing the IgE level of a person. So she will get her IgE levels tested, but for the purposes of my model, I'm not modeling IgE, I'm kind of modeling the process that happens before that switch. Mm-hmm. Yeah, and that's kind of, that's where you're in kind of like a tough spot, right? So you have, I'm sorry? Oh, I'm sorry. The question is, wouldn't you need like those real world, wouldn't you need real world results to be able to compare, you know, when you're training data, don't you need those real world results to train the data on? And so that would be great if we had that, but unfortunately we don't most of the time. And so I think the idea that I was getting at was if we can get to a point where we've got a model that we know is really approximating this really, really well, then we know that the numbers that we have are pretty close. You know, I mean, you're stretching it, but it's all theoretical, right? It's all just ideas, and it's ideas to get you closer to an answer. So it might not be like the cure for food allergies, but maybe at the end of this we know that, oh, if somebody drinks a glass of milk and then we introduce this virus at this time, it will completely change the way that they react to this milk and we won't have to, or they can begin testing that. I mean, who knows? That's kind of the impact something like this would have, I believe. Does that answer your question? Okay.
Are there other factors that influence this, like age and different things, or is it, I'll just stop there. Are there
Okay.
other factors that influence it?
Yeah, he asked if there were other factors that influence these population sizes for the model, and absolutely. Everything does, it seems like. Age, health, all of that's going to matter. For the purposes of a mathematical model, it's very oversimplified because you can get really, really deep in the weeds with it. And once you get that deep, it's almost impossible. You can't approximate a large group of people and what would happen with them if you're focused on like what would happen with a specific person, you know? So.
So, wonder if there's a component of this that has to do with microbiomes, medicine.
Yeah, I mean, and I don't know enough about that right now, but oh, he asked if there was a component to this with microbiomes, and I think that's a really great question, and I don't have an answer for it. Yes.
Kelley, as you continue with this, so you did most of this in our studio, are there other tools or technologies you're looking to use? Are there any things you just don't have access to or something that you want to use to continue this work?
Sure. So one of the things I talked about was visualizing my results, because that helps me a lot in determining, you know, what am I looking at here. And so I think that is going to be the biggest hurdle, and that's kind of why I talk about, you know, possibly using some of these other tools to investigate the results, because you can't, I mean, you can't look at something in 5 dimensions, right? So I would say visualization tools are going to be key, John. And then I think, I don't know, I love R so much. I just want to do everything in R.
You can certainly do everything in R, but you might want to look at Google Facets.
Google Facets, okay. He suggested using Google Facets, which I know nothing about, so I'm going to have to look into that. Thank you. Thank you so much. Yeah. Oh, the system of equations? Yeah. No. You had a bunch of differential equations. Mm-hmm. Those were all able, and it was just how possible that you could find them all in the literature. Were you able to get them all, or did you have to derive any yourself? Yeah, so she's asking if I was able to get that series of differential equations from some papers and other published sources. In this particular case, no. I did use papers and published sources to get my data together to build the model, but I actually put the model together and based that on my own research of the processes that are happening when somebody ingests an allergen.
Oh, okay.
Yeah.
So, if you're doing this all based on dairy,
Mm-hmm.
if you get this kind of down a little bit, like some of the other data you're finding, could you, I guess, use it to swap out dairy, kind of glue them together and kind of
Yeah, I would think so. I don't know enough about the other allergens to know what is involved in those processes. If it is, in fact, IgE is involved in all of those. I know, like in this case, mast cells are a big deal, but eosinophils are a big part of allergies, but maybe not as much with milk because they're usually kind of in the lungs and things like that. So it just kind of depends. He asked if I invented the term pseudodata, and I would like to say yes, because I started calling it that, but then I was like, I should Google this and see if I'm saying something that is not what it is. And I Googled it, and it is what I was referring to. So, yeah, no, I didn't invent it, but it's a word.
So have you thought about trying to decompose the time series model to try to find some of the natural trends and correlation between some of the factors and then comparing that to a normal and non-atopic
Sure.
individual and use that as maybe a proxy to start estimating that?
I have thought about using a time series component because obviously we have time data, right? It makes sense. But as far as that deep into it, no. And I want to write down everything you just said. So come talk to me afterwards. She asked if I wanted to, she asked a very interesting, complicated question about time series data that I'm going to get more information on later. Would you like to repeat it?
Sure. I asked if she thought about using a time series model like STL ring or other models to decompose the natural trends and find some factors in those trends that could she compare to a normal person's reaction to things and then using that as a proxy to estimate the parameters.
Sure. Yeah, so essentially what she's suggesting is using a time series model, using a decomposition of a time series, and looking at trends on that data and comparing it to somebody that does not have food allergies so that we can get a better idea of parameter estimation, which sounds awesome. It's a good idea.
So I've done some graphs on that 80-20 rule, and that's sort of like where it's 80% of your profit comes from 20% of your product.
Mm-hmm.
And they look exactly like those graphs that do that. Right?
Mm-hmm.
And I'm wondering if that's interesting in some way, like 80% of what's happening in the algae is actually something. But it definitely looks like 80% of the effect occurs in the first 20% of the time.
Right. Yeah, I know you're absolutely right. I hadn't thought about it that way. Oh, I keep forgetting to say the question. He is referring to an 80-20 model of 80% of your profits come from 20% of your products. And so he's saying that those graphs look really, really similar to the graphs that I put up earlier, and that most of the action is happening right there at the beginning. And so there is maybe some interest in what's happening right there versus what's happening after, correct?
Yeah, if you can cut that first 20% effect, then you would have almost no effect at all, right?
Yeah, that's awesome.
Where are you, when you got the equations up there,
Mm-hmm.
where in the equation, where's the feedback?
You mean in the model? Yeah, we can go back and look at it. So I wish I could walk over and point, but so if we start at the top, anywhere you see a DM, that's going to be a dendritic cell with milk, and that's how we're seeing these produced, and then they're also leaving the population as well. And then you come down to a dendritic cell and IL-4, and that population is directly impacting the population of the dendritic cell with IL-4. And then we see below that dendritic cell with IL-4 is affecting the Th2 population. And then we see that the Th2 cell is directly impacting the IL-4 population. And so we have this sort of, this feeding down of the populations. Is that what you were asking me? I'm sorry. I think he was asking about the feedback of the model.
More people
Mhm.
Did anything come up in your research, like, was that something that had to do with a little bit dendrites are formed, like proteins in the cell, or reason?
So she was mentioning that some people are born with a predisposition to be able to process milk proteins better than others genetically, and asking if I came across anything in my research that would maybe explain that. And the short answer is no, because I wasn't really looking for that right now. And there's so much research out there. And so what I was really specifically looking for was information related to the Th2s and their relation to the IgE. So, no, I'm sorry. Anyone else? Okay, so the B cells are not part of my model. Right. Right, right. But what causes the class switch of the B cell to produce the IgE is the IL-4 cytokine. And so what I'm doing is I'm measuring the IL-4 cytokine and the Th2 cells that produce that IL-4 cytokine, because those are going to be what is going to cause an increase in the IgE population. I'm sorry. Yes. Any other questions? No? All right, one more thing, guys, and then we can be done. Okay, this has nothing to do with my research right now. Maybe it will in the future, but I wanted to bring it up because I thought it was really cool. I've been reading about it. There's a new neural network ODE solver. It's using an ODE solver. I don't know a whole lot about it, and I really don't know a whole lot about neural nets to be able to speak super intelligently on it. But I do know some of the cool features, some of the novel features that they're talking about is you can use it on discrete time data, which I believe is a new thing. And then also you can look at it at a precision versus speed. So you can kind of pick and choose. Do I want it to be really, really fast, or do I want it to be really, really precise? And you can kind of tweak it and move it back and forth between those two things and kind of get really what you're looking for there. And so here in the, this is a picture from their paper that they wrote, but you can see the difference there between a recurrent neural network and a latent neural ordinary differential equation. And so it's just a new way to solve a neural network type of problem and build a model. So I wanted to share it because it's interesting, and if you guys are interested in it, then you can look into it more, but I wanted to mention it because I thought it was cool. But that's all I've got for today, you guys. Does anybody have any questions anymore? Great.